Okay, we're just about ready for your homework. So not everybody got this quite right last time. There's a handful of you that didn't, so we'll review it again. The details are important because I have so many to handle. You take your whole stack like this, fold it so you close up the front page, and here's the key that some of you missed. Turn the open side to the right. Turn the open side to the right. And then your heading goes here. So when you're holding it in your hand, it should look like this. And here's our heading. Name, 270, 1030, 829. Okay, so in terms of posting, I'm going to post solutions online, but there's still lots of people in both classes still enrolling. Like I have in my more earlier class, I have 2 or 3 brand new people this morning. So I think this today at 2, like the last chance. Yeah. So after the roster is set, then I'm going to start for these first 2 assignments. I'll post solutions, and normally then I'll be posting the day right after you turn it in. It should be available to look at those solutions. Okay. We need class time is precious. We need every moment. So please get your questions answered. Like I said, I'm not going to talk a lot in class, go over homework problems. So you need to take a responsibility for yourself to look at those solutions and then see what you're still having trouble with and get help. And so I put office hours here on Blackboard. It's the inevitable question that many of you will have throughout the semester. When are your office hours? Because you haven't visited yet. So you can just go to Blackboard. And I put up mine, which are Monday and Wednesday, 1:15, and Tuesday at 11:30. And then Marshall, your TA, he's actually sitting in on the previous class, so he knows exactly what I'm covering and how I'm doing it. One of the 2 of us is going to be your best bet for help. Okay? If you go to a different, like you go to the math tutoring center, they may be able to help you, but they may be unfamiliar with kind of what we're doing. So just be aware of that. So he's sitting in on class, obviously I'm teaching it, so the 2 of us are your best, like I said, your best line of defense for help. I've also, up to date here, I'm going to try to still connecting. Okay, so then there's another here in the menu, class videos. The first one is just the channel, so if you can just go to the channel and browse all the videos that I got, but then I'll be posting below here, I post them by the day. Okay? So that can be helpful to go back and review something that we talked about that you didn't quite capture with your notes, okay? All right, so let's turn, and everyone got your heading on? We're good? So pass them straight up. Oh, a reminder again, if you're tearing out of a spiral notebook, it needs to have a perforated edge. So you've got to get all the chunkies off. Pass them on up. So far we're really trying to focus on quantities, okay? And specifically looking at 2 quantities and how they relate together. This is kind of the underlying idea which calculus is built upon, okay? And it's really, in terms of pre-calculus, it's kind of the whole goal of pre-calculus is that you really understand quantities, especially how quantities change together. So we're going to kind of transition from the static bars that you've been using. Even though those bars have been static, you still should have gotten the kind of the feel of changing quantities and what we've been doing with the homework, looking at different corresponding pairs of the 2 quantities. So now in this particular case, I can grab on to the red bar in various length, okay? The blue bar is going to vary correspondingly to how I vary the red bar. So I have a question for you. if I say make I don't know, say like this. If I put the red bar, if I extend the length of the red bar to there, the question is, where is the blue bar? What's the length of the blue bar going to be? So what I'll do is I'll just give you choices. So what I want you to do is find a partner. I, J, K, what's the alphabet? L, M. Okay. Well, just one more, N. So these are like just to give you a reference on location. So I'm going to extend the red bar to here, and I want you to decide, and this is just, you're just estimating, right? So you're using reasoning to do your best estimate. Where do you think the blue bar will be when I extend the red bar to this distance? Talk amongst it with a partner, okay? See what you think. Okay, now let's go over here to the wall. How about you in the white shirt there? Yeah, what'd you think?
Me and my partners guessed like F-ish.
Which?
F.
F. Okay, and what was your reasoning? How'd you come up with that?
Because the red bar, like we estimated that it's like doubling in length with like a little bit more on the end, so we
Okay.
just went with the blue bar and then added a little bit.
She said double and add a little bit more. You don't have numbers, so this is the kind of reasoning that we need to do. So she said, what do you think of that? She said, if I move the red bar to there, it's like doubling and adding a little bit more. Okay, so then she did the same thing with the blue bar. So doubling would be about where? Okay, and a little bit more? So you said F, okay? So that kind of reasoning is what we call scaling. We're scaling both quantities together. This one gets scaled up by a little bit more than twice its length, so therefore that one has to be scaled up by a little bit more than twice its length. Let's see if she's right. Sorry, it's hard to get it. There, that's the closest I can get to the spot I marked. Okay, so we're estimating. Her reasoning was good, but we need to go a little further. Okay, we just need to go a little further. So, but the reasoning was good. Okay, so what if same question, but what if I gave you this? Is there a different way to think about this? What if I told you that the length of the red bar was 4? At the beginning, and then this was 12. And then I told you that this was right here is 10. So is there a different way to get the same? So we talked about scaling. However we scale up that length, we're going to scale up that length. Is there a different way to reason and get the same answer? See if you can. Yeah, go ahead. Okay.
It's timed by 2.5. So
Right.
then the blue bar has to go by 2.5 too, so we do it
Great reasoning. That was great. But that was the exact same thing that we said before. Okay, so that's the scaling reasoning. But it was well said. Very well said. She said 2.5 times 4, therefore 2.5 times 12 would put us out here at, what is 2.5 times 12? 30. Okay? Is there a different way to see that the blue bar is going to end up being 30? All the way in the back.
4 is 1/3 of 12. So
Okay.
10 would be 1/3 of 30.
Okay? Is that what,
Yeah.
so start off by looking, what are the relative sizes of these? So the relative size, the blue one is always what? How is it related to the red one?
It's larger. Why I use 3 times.
At least?
Well, 3 times.
Exactly. So the blue one is exactly 3 times as large. So if I make the red one 10, then the blue one will have to be 3 times the length of the red one, or 30. So you see that those are different ways to reason about it. The first way was scaling both the same amount. The second way was using the relative sizes. If we know they're always 3 to 1, they're not always 12 to 4, but they're always 3 to 1. So if the red one is 10, then the blue one would have to be? I can't get it. I picked a spot in between. So pretend that's 10, then this would be 30. Okay? Let's try a different example here, a little more practice, and then we'll... All right. Okay. So I'm going to move the red one way over here. So you need to have good estimating skills. So move the red one there. Where will the blue one end up? So you can start talking as I'm writing letters. Go, take a minute to talk about it. That's a hint. Okay? Somebody new. What do you think? Right here.
We reason that it'd be between D and E
Okay.
because we'll look at it from 2 ways. Because the red, we believe the red is about 1/5 of what it's going to be. So you could times the blue by 5,
Okay.
and that would put you around D and E. And we also thought that.
All right, so that first, he said he thinks the red right now is about 1/5 of what's gonna be, and therefore, what are you gonna do to the blue one?
1/5 by 5.
Yeah, so he wants to, if we're scaling that up by 5, he's gonna scale the blue one up by 5 too. So what kind of reasoning is that? Scaling both, right? We're multiplying both by this scale of 5. Okay? And you wanted the other kind too, go for it.
We also thought the red line is about 4 times as great as the blue one.
Okay?
So if you take like the final point of the red one,
Okay.
divide that by 4. That also kind of puts it between D and E.
Okay, did you hear what he said? Yeah, so the first time he said, how much did we scale this up by? Times 5. Therefore we gotta scale the blue one up by 5. Then he said, what portion of our final value, or sorry, what is the relative size of the red and the blue? And so the blue is always about 1/4 of the red. So looking at the final value of the red, what's going to be, so that's why I drew this dotted line, what's going to be 1/4 of that? So again, what was the letter you thought?
D between those.
Between D and E. Is that what most of you thought? Okay. Let's see. Pretty good. Okay, yeah, and indeed this is exactly, the blue one is 1/4 of the red one, always in relative size. So it's always in a 4-to-1 ratio. Okay, anybody have a question about that? So in the last question of your homework, it said, and I reread the homework question, and it wasn't really clear, and that's unfortunate. But that problem won't be graded. Don't worry. But what should have been clear in that last question is, if we just take the blue bar is dependent on the red one. It's always 1/4 the length of the red one. Just take the blue one, flip it 90 degrees, standing straight up, and then we're going to put it on the end of the red bar. And then we're going to do the same thing we did before. We're going to let that red bar change. So the red bar stays the same. Take the blue one, flip it up 90 degrees, and attach it to the end of the red bar. And then we're going to, again, let that red bar change. So talk with your partner. What would you imagine that you're going to see if I did that? If I flipped the blue onto the red and then varied the red, what do you imagine you would see? So explain to your partner. Okay, so the first part should be, the first step in this was I was going to flip it onto the red bar. Did you see that? So here it was. This is what we're used to with our looking at our quantities this way, but now I'm just going to take that second bar and flip it on, so attach it to the end of the red bar. It's always going to be on the end of the red bar. And now I'm going to say I'm going to increase the length of the red bar. What do you imagine you'll see when I increase the magnitude of the quantity of the red bar? Yes, sir?
You'll see the blue bar go up in magnitude as well. You kind of have a linear relationship across the rest.
So he said, if I increase the red bar, that blue bar is going to get taller too? And he said more than that. He said, so if we were tracking a point there on the top of it, what do you expect that point to do? Rise, okay. Just the point's going to go like this?
No, it's steady.
Okay. Let's take a look. It kind of speeds up once it gets the hang of it. Okay, so why is the blue bar getting taller? And also, yeah. So they're in a 1-to-4 ratio, and if the red one gets taller, that blue one's going to get taller too. It's always 1/4 of it. It's always 1/4 of it. So if I stop it, say right here, and I say I attend to the top of the blue bar, what do I get? What is that a representation of? I drew a green dot or point. What is it a representation of? Somebody knew? What's it? Okay, but okay, that's actually what you said was the length of the blue. The length of the blue is a fourth of the red. But what about that point? Just the green point. Yes, ma'am. Okay. So and then what does the point represent? So she wants to think this is a good idea. If this was a graph. Yes, sir.
I think the point represents a function where the slope is 1/1.
Just the one, we're going there, that's where we're going. Just the one point. What does it represent? Yes, sir.
Coordinates of the x on the graph or the y output of that x.
Okay, so instead of talking about x and y, just talk about the quantities that we introduced. Does that make sense? Does the question make sense? Yes, ma'am. Yeah, so it's that green represents kind of a package of information, okay? It represents the value of the red quantity associated with the value of the blue quantity. That green dot represents that. And what happens if I increase the red bar? What do I get? I get a new associated pair of the blue and the red quantity. And what is, in terms of that association of the two quantities and that association of the two quantities, what's the same about those? For any point that I pick off the top of the blue bar. Tell me specifically what's the same.
The ratio.
Yep, their relative size. So every time I change that red bar, I get a new height for the blue bar, and the top of the blue bar gives us a point. And that point represents the red quantity and the corresponding blue quantity together, both. Do you see that? Y'all seen this in the sky? What is this?
Contrail.
What's that?
A contrail.
Contrail, okay, so I'm calling it a vapor trail. This is a different way to call it. And so, a couple of vapor trails. So, when you see that vapor trail, what does it represent? What is it showing you? You look at that and you think, oh, if I point to a point on that vapor trail, what does it represent? Where the plane was, right, at a certain point in time. So we know that this is where the point, that think about it as all the locations of the plane. All the locations of the plane as it went by. Okay, there's a plane I don't want to be on. Okay. So what do we know about this plane? It flew the shape of a heart, okay? And so we know all its locations based on the trail that it left behind. So imagine now we're going to put a plane on the top of the blue bar. I think. There we go. All right, so I'm going to put a plane on the top of the blue bar. And then the vapor trail of that plane will represent, just like in a plane, it'll represent where the plane has been, right? Where it's been. Ooh. But what is the point? The point is, what does that trail represent? Now I'm not asking. So yeah, this is one is straight, but I'm just asking about graphs in general. Okay, graphs in general. This is We're trying to represent what a graph is. Does anyone want to give it a shot? What? Yeah. Okay, a continuous path of what? Talking about what we talked about before. What is that made up of? Points. That's what a graph is. A graph is all the points. Each one of those points represents, tell the person next to you what each one of the points represents on that trail. Go. What does each point represent? Here's another way to think of that vapor trail. Okay? What does one, so if I came here and I went to that one point, what does that one point represent? Somebody new? Practicing. Yeah? Does it represent the distance? It's not what we said. The plane is just a visual to show that we're just marking off where the top of the blue bar has been. But these quantities don't have to do with the plane. Does it make sense? So again, back from what we said, what does one point represent? Yes, ma'am. Okay, it's representing two quantities, a specific red quantity and a corresponding blue quantity. That's over here, I guess. So that's representing, when we pick the red quantity, say at 5.5, this point then represents the corresponding blue quantity of what related to 5.5? How much of 5.5? 1/4. So if you show all the points, you get a graph. That graph is showing all those individual points. So, for instance, let's do a totally different kind of graph here. So here's a totally different kind of relationship. Oh, I didn't turn the points up. I gave it away. All right, here we go. So here's a much different kind of relationship. These are not a relative size relationship, okay? So as red increases, blue increases, then decreases, then increases, then decreases, okay? But the point is the same, that the graph is showing that relationship between the red quantity and the blue quantity. And a point, and what is that graph made up of? Points. Try to stop not seeing it. Okay? So the conversation is not specifically about the fact that that thing was a line, but just that what is a graph? Okay? It's mapping out, each point maps out a certain quantity, which we call the red quantity, and the corresponding value of the blue quantity according to whatever relationship they're in. Okay, so let's go back to that one though. So here's the one we were working with. So let's put some context on this. Let's suppose that the red quantity is the volume of water in a bottle in milliliters. Okay, so we got a bottle in front of us, and we're gonna pour water in, and so this red is representing, the red bar is representing how much water we poured in. Okay? And then the blue quantity then, because of the bottle, the blue quantity is determined. It's determined by how much water we put in, right? Because that bottle is a fixed thing. Okay, so it's determined as, and we want the blue quantity to be to the height of water in the bottle. In centimeters. So which one is the one we have control over and which one is determined? Which do we have control over?
Water.
The volume of water, how much water we put in. We can put in 3 milliliters, we can put in 8 milliliters, we can put in 7 milliliters. And then based on that, we have a determined result, which is our blue, which is the height of water in the bottle. Okay, so we often call this red because we have control over it. It's independent of anything else, so we call it an independent variable. And normally that's called, what variable do we use? So x. So I'm showing, you can kind of see it there. So I'm showing that the value of that red bar down there, the length of the bar is representing the amount of water we put in, and that's x. So we're going to call it x. Okay? The height of the water in the bottle is centimeters. Once x is chosen by us, then boom, that height is determined. So if I choose it to be 4.9, boom, the height of the water is, what is the height of the water? If I choose the volume to be 4.9, what would the height be?
4.9 force.
Yeah, so it would be 1/4 of that, right? We said this relationship was always 1/4. So it would be 4.9 over 4. Okay, so it's a determined thing. So what we use for that is, we use the notation, you've seen this before. We're going to kind of flesh it out in depth here. F of x. Okay, so you've seen this kind of thing before, you've done lots of problems involving it, but we really want to talk about what it means. So some more room here. Okay, so x is what we call the input. That's our independent variable. We have control over that. So you'll see that's in the parentheses, right? This is not multiplication. It's not f times x, right? So x is the input. F is simply the name of the function. We can name it anything. Okay, we could have named it h, and that would be a little more descriptive because we know that we're getting height from this. So then the whole symbol together, the whole expression then, that's the output, or in this case, that's the height of water. But it's more than just the height of the water. It's the height of the water when what? So the height of the water can change, right? The height of the water can change. It could be 3 centimeters, it could be 6 centimeters, it could be 8 centimeters. So what particular height does it represent? When what? Yes, sir?
When x is at any given value.
Okay, yeah, so when the volume of water is x. So whatever volume of water we put in there, that thing represents the height for that volume of water. So in this case, it's allowed to vary, any value of x. So it's the output or the height of water when x milliliters are added in the bottle. Okay, the right side over here, this is called the rule. The rule is that deterministic relationship that allows us to find out what the height is when we have that many milliliters of water. So we got the name, we got the input, that whole expression there represents the output. And in this case, that's the height of the water when X milliliters are put into the bottle. Okay, the right side is the rule, and that rule is what allows us to find that height when we know what the water volume is. Okay, so what I want you to do with your partner is explain what these things mean. Three items there. So, with your partner, tell your partner, explain what does that whole thing as one symbology. What is that? What does that represent? What does this whole expression represent? I'm not looking for any computations or values. I'm looking for statements and phrases. What does that what do each represent? Go. I got two more for you. Keep going. Two more. F of A plus 2. We want very precise meanings for each of these. Very precise. When we get to the back, there may be some rows I didn't give enough to, so pass left and right. Okay, here we go. F of 2, we'll start easy, but then we get trickier. So F of 2. Volunteer, yes ma'am. So she said it's going to be that thing represents the height of the water when you add 2 milliliters in the bottle. Agree with that? That one's easy. We can do it in our head. So what is the value of that? Yeah. So it's going to be 1/4 of 2, right? 1/4 of 2. So the value of that is 1/2. The meaning of it is the height of the water when we put 2 milliliters in. So this is a real easy one. Now after that. So here's your chance. Take an easy one. Who wants to explain? F of 7. Go.
20
when you put 7 milliliters of water into it, the height of the water
What the height of the water would be when 7 milliliters are in. And what is the height of the water? What is that equal to? 1/4 of 7. 1/4 of 7. Could write it like that. Or, but what I originally asked you for was the meaning of it, which is the height. Okay. This is harder. So who wants to give a shot at that? Precise, very precise. Yeah, go ahead, sorry.
The height of the water when you put in 7 milliliters and then take out.
Okay, so are you taking out 2 milliliters of water after you put 7 in? So then is it the same as the height when, if you were to put 5 in? It's the same as the height if you were to put 5 in. Is that what you were going to say? You, in the white shirt, you had your...
I was just going to explain.
Okay, you go for it.
Well, since we have now 2 outputs that we need, each representing a different height,
Okay,
calculating them independently
okay.
would be my first approach.
Okay, so you have, right?
Get 7 fourths for the height of the first one, and then 2 fourths for the height of the second one.
Okay.
And then you just subtract them and get 5.
Okay, so if you were to subtract the height at 7 minus the height at 2, what would that be? What, in this context, what would that mean? Yes, sir.
Is it the change in the height of water between 2 and 7?
He said the change in the height of the water between
7 and 2, or 2 and 7 milliliters?
between if you had 2 milliliters in the bottle or to when you had 7 milliliters in the bottle. Go ahead.
Would it just be 1/4 of 5? According to the
Okay,
pattern?
so you're going back to f of 5. So here's the question. Is it f of 5? This is really important. So question, is it f of 5? Is it the height of the water when 5 milliliters are in the bottle? Yes or no?
Yes.
Some are saying yes. In the corner.
I think that it is in this case, but it's not necessarily always.
Okay. So you're saying that the number, the values are the same, but the meanings are different. Yeah, so our real question here, exactly, our real question here was, what is the meaning of f7 minus f of 2? So he was laying it out nicely. If this is the height of the water when we have 7 milliliters, and this is the height when we have 2 milliliters and we subtract, here's my very artistic bottle. So for 7 milliliters and here's for 2 milliliters. If we subtract those, what do we get? What's the, in context, not a value, but what does it mean? The difference between the heights, which would represent someone said the change in the height. That's what it is. It's the change. Remember we said that subtraction was one of the key operations in calculus because it represents the total change, the change in height. And she made a very good point in the corner. That change in height does not necessarily have to be, it could be that change in height. That's what this means. That is not necessarily what the height is when 5 milliliters are added. That's a totally different thing. Okay, so make sure you watch out for that. So maybe the values are the same, but their meanings are not, and that's what we're talking about, meanings. The meaning of this is, if you take the height at 7, subtract the height at 2, you're going to get how much the height changes from if there were 2 milliliters in to when you went up to 7 milliliters of water, and how much the height changed. This is the height when you put 5 milliliters in the bottle. If we had a curvy bottle, these two would be different. These would have different values. Okay, what about f of a? Quickly. What's that? Tell me.
Height of the water in the bottle when you add a amount of water, milliliters of water.
Yeah, the height of the water when you add A milliliters into the bottle. Okay? What about F of A plus 2? Somebody knew. Somebody knew. Right here in front. What would F of A plus 2 be?
It would be, it's just the height of the water when you add 8 milliliters and always adding 2 more milliliters.
All right, yeah, that's pretty good. So it'd be the height of the water if you had those 8 milliliters in, but then you also had 2 more milliliters. So you had the 8 milliliters, you add 2 more milliliters, and then you find the height, right? That would be that height. Okay, take a look at the handout I gave you, which you just have a couple minutes to read through, think over before you do it for Friday. This homework kind of brings together everything we've done so far. So I'm giving you 2 photos. The first photo corresponds to the first column of questions. The second photo corresponds to the second column of questions. But they're basically the same questions. You're just doing the same, except there's one difference in just the number in part A. That's the only difference in part A, okay? So you're going to answer the same set of questions generally for each photo. So when you look at that, say that first photo of the SUV, is that moving or sitting still? Obviously moving, okay? And so how is it possible that the camera can show that it's moving? It's blurry, okay? But so what is it about the camera that's showing the movement though?
It captured multiple points.
What's that?
Captured multiple points.
Okay, yeah, so it's capturing not just an instantaneous point in time, but it's capturing an elapsed time. That's the information that I'm giving you below the photo there. It says, this photo was taken when the SUV was in a 10-foot wide crosswalk, and the camera shutter was open for 1/40th of a second. Okay, it was open for 1/40th of a second. So that shutter opens for an elapsed time, and so the light enters over that period of time, and so therefore, if something's moving, it's going to look like a blur. You see? So you can use the blur and that information that the sidewalk is 10 feet wide, the crosswalk, and how long that shutter was open to answer these questions that I've given you. Okay, so they're questions about quantities, they're questions about speed, they're questions about function. So if this is now bringing together everything we've done so far, and you're going to do this for Friday. So why don't you got a couple minutes? I would read over and think about it, and see if you have any questions before you're out of my presence to help you. Okay.
So where do they do that, like, when they press the button that is entering the crosswalk, right when they press?
No. You got to think about it. So think about what you're seeing. So when the shutter opens, and then just a hair of a time later, the shutter closes, it's going to capture what was in view. So you're not assuming that it starts at the beginning of the crosswalk. Yes, sir.
There's a couple others in the back.
Are there any more?
The original image, not the.
Any more of the first one back there? Stack. Should be the same amount of each. Everyone got the photos, but you didn't get the questions. Okay, let's see it. How many people need it? Just 2. Okay. Yeah, I'll get you some, for sure. Or I'll just post this. I'll post this, everyone's got the photos, is that right? So I'll just post it on Blackboard. You can look at it. Okay, any other questions about it? Is the task clear? So I haven't done an example like this. There is a problem-solving element to this. You're going to have to think and figure it out. Once you get through that, then this is bringing together everything we've done so far. See you Friday. That's due Friday.